Well, good evening, AP Physics students. Mr. Curson coming at you here. So for tonight's video, you should have gotten a handout like this from your instructor about rotational motion. So you'll want to refer to this during this unit. This little guy will be your best friend. And you'll notice there's some blank spaces here that we're going to try to fill in. All right, so we got some blank space, just like Taylor Swift. T. Swilly, she's my favorite. Okay, so we are going to talk about rotational or angular motion today. So let's just define things here a little bit. So here I have a CD that my mom burned for me about the Rosetta Comet mission. And so when we talk about rotational motion or angular motion, we're talking about things rotating on an axis like a CD or a DVD. We're not talking about circular motion where a point particle goes in a circle. Now, as it turns out, the two problems can relate to each other, but in this unit, we're going to be talking about things spinning on an axis like this. So we need to define some variables here, all right? So the first thing when you're talking about spinning is you want to know how far as an object spun, or at what point in the turn is it. So if I say this is 0 degrees, I might spin this way 90 degrees. Well, anyway, our symbol here is theta for angular position, right? And you can also have delta theta, meaning change in angular position. And you can measure that either in degrees or radians or revolutions. And we'll talk a little bit how to convert between those units. So theta is our symbol for angular position. Now, we will also talk about angular velocity. So angular velocity is how fast something is moving. One measure of angular velocity is RPM, revolutions per minute. So how many times has it spun in 1 minute? Another unit, the SI unit, is radians per second. If you're wondering what unit should I use for a problem, you will always be safe using radians. All right, radians is your best bet. You'll never be wrong if you use radians. Now, just like in linear motion, you know, final speed is equal to initial speed plus acceleration times time. We have an equation like that for angular speed. So final angular velocity is equal to initial angular velocity plus angular acceleration times time. Angular acceleration, what's that? So that is the Greek letter alpha, right? A is for alpha, right? And that's the rate at which something is accelerating. So for instance, I might go from 0 radians per second to, 2 pi radians per second. And so I would have a rate at which I am accelerating. We'll also talk about next video when we get into angular dynamics here, how angular acceleration is related to torque and rotational inertia. For right now, we're just going to, for this video, we'll talk about angular quantities in terms of kinematics, just describing the motion here. All right. So make sure you got these equations written down on your notes there, and then we're going to transition here and do a problem here as an example of how to use these different units. So the problem we're going to do is out of chapter 8, number 16. And the problem reads here, an automobile engine slows down from 4,500 RPMs, revolutions per minute, to 1,200 RPMs in 2.5 seconds. Calculate its angular acceleration, assume constant, and B, the total number of revolutions the engine takes in this time. All right. So that's our problem, and let's dig in here. Okay. So what do we know? First of all, it's always good to have some sort of diagram here. So if I were to do a quick diagram for this, if it's an engine, it means there's a piston attached to a crankshaft here, and the crankshaft is going around and around. So I have something spinning around. In general, just like in math class, the counterclockwise direction is defined to be the positive direction, and the counterclockwise direction is typically defined to be the negative direction. All right. So let's write down some things we know here. We are told at the beginning that the initial angular velocity is 4,500 RPMs. All right. We're also told that the final angular velocity is 1,200 RPMs. And I think I'm going to go ahead and convert these into radians because that's kind of my safe unit. All right. So let's just kind of go off to the side. And so if I have 4,500 revolutions per minute, I can simply use dimensional analysis to convert that to radians per second. So in one revolution, there are 2 pi radians, right? So one loop around the circle is 2 pi radians. And in 1 minute, there are 60 seconds. So we see we've got everything canceled out there. And if I type that into my calculator here, rounding, I get about 471 radians per second. We could do a similar type calculation with revolutions, 1,200 revolutions per minute. And likewise, we would get, let's see, this turns out to be rounded about 126 radians per second. All right. Okay, part A. Oh, and pardon me, I missed a variable here. We were told that this occurs over 2.5 seconds. Again, you can see why I wanted to convert these into seconds. If I have this time in seconds and that time in minutes, my equations won't work. All right. So, what equation should we use to find angular acceleration? Well, just how acceleration is equal to v minus v naught divided by time, I know that alpha is equal to omega minus omega naught divided by time. If you know your linear equations, usually your angular equations follow right from that. All right. So let's plug in some numbers here. This was 126 minus 471 divided by 2.5. And if I type that all in, I get about negative 138, or with significant figures, which there should only be 2, negative 140 radians per second squared here. All right. Here, the negative direction means that the acceleration would be occurring in the negative direction, meaning that it's slowing down. All right. So that is part A of this problem, and let's jump ahead to part B here. All right. So in part B, it wants to know through what angle does this run. All right. What angle does the engine turn through as it experiences this change? So I could use for this one, this equation, delta theta is equal to omega naught t plus 1/2 alpha t squared. So again, think of this as like delta x equals VO t plus 1/2 at squared. All right. And so plugging things in here, we get 471 times 2.5. Plus 1/2 times negative, I'll go ahead and plug in, instead of 140, I'll plug in 138, just to make sure I don't get too much roundyitis there. All right. And plugging things in here, I get delta theta is equal to 746 radians. But the book actually asked how many revolutions does it go through. So let's convert that back to revolutions. So 1 revolution is 2 pi radians. All right, so the radians cancel here, and that turns out to be about 118. So, oops, I'm off the page. All right, here we go, Kirsten. So delta theta ends up being 120 with significant figures revolutions. Okay, so that's our answer to part B. Nice work, physics students. Make sure you keep your note sheet filled out. And for our joke today, I want to show you what I got for Christmas this year. I got a nice coffee mug here that I can drink coffee and green tea out of. And it says, "Everything tastes better with dog hair." In it. And this was wrapped under the tree. And it said from Raven. But I have a feeling like Mom Kirsten might have had something to do with it too. So, nice work, physics students. We'll see you tomorrow.